For the agenda of the webinar, I will be going over the following things. I will briefly introduce a topic. I will provide a conventional definition of the driver state monitoring. I'll show you guys the need for the technology with some stats. I'll show details about how this particular technology contributes to the evolving need for the increased level of autonomous driving autonomy. Then I will go over a comprehensive overview of this topic where I will provide the key components that are involved in driver state monitoring and provide you a full-blown view of how a generic driver state monitoring system works. I will introduce some of the standard techniques that we use today in the industry to implement this design. Then we will go deep down into each and every single techniques and how they are implemented at a high level, sensors that are being used, and going over the state-of-the-art technology of who are the leading providers of this particular technology that we have. We'll go over, I actually picked a few of those OEM product lines. We will go over them to see how they have used these technologies and what is upcoming in the trends for the future. In the recent advancement sections I will go over, I picked a couple of them to see, to show what are the recent trends and the research that are going on and how they will be adopted by the industry. While the technologies are always developing and advancing, there's an inflection point in which the industry gets that and commercializes into a vehicle. So we will see some of those latest ones. And towards the end, actually, I'll talk a little bit about possible career opportunities where I'll be focusing on functional aspects of where you get to work on this thing. Without any further ado, I'll go introduce the topic. So what is driver state monitoring? A simple conventional definition is a driver state monitoring system is a vehicle safety system that primarily detects two key components of the driver behavior. One is driver distraction, and the second one is the drowsiness behavior of the driver. These are the two key components that we want to detect. And based on the detection, the system provides alerts, warnings, and other way of indicating the driver there's a potential danger or a hazardous situation is ahead of you. So that is primarily what a driver state monitoring system is. In the system engineering point of view, this needs a bit more elaboration, but this is a very much more of a generic definition. If you do a Google search on the technology that we have, you may find technology we have today, because this particular system is on the brink of a big evolution, given that we are moving towards a higher level of vehicle autonomy, which I'll talk in details. This thing, I want to go over why part, so the need for the technology, so why we do what we do. Knowing this thing helps in the long run to answer several questions. So the primary need for this technology came mainly because of what I show in the right-hand side here, is the distracted driving and drowsiness related accidents. The statistics over here shows some numbers for India and the US. So in India, we have in 2019, roughly about 4,945 deaths. And in 2018 in the US, we can see that for the drowsy driving, there's 795 deaths. And for distracted driving, there's 2,841. And also it shows there's a numerous number of accidents and fatalities involvement of the driver who are distracted and feel drowsy. It's a staggering number all around the world, but I've given only the numbers for India and the US, but all around the world, it's roughly on an average of 1 in 4 accidents around the world is caused by distracted driving and drowsiness only. So that's why this technology is a key role in playing and improving the vehicle safety as a whole. On the left-hand side, I can show you there's another thing which induced all these things. It's the response time of a driver when the driver is distracted. Studies show that on an average, the driver who is not distracted or not under the driver is about 1 second. But if you are under any of these influenced distraction, for example, you have a oh, if you drink over a certain limit, it's possible that you're 13% more, your response time is going to be 13% more than a normal driver. And as you can see, the handheld phone usage is the highest one, which shows a 46% increase in the driver response to anything that happens in a vehicle. And we all know the accidents can happen within less than a second because they are accidents. And the driver response time increases over the period of time when the driver is under any of these particular influence. So that is two main things that we see why the initial need for this technology came into play. And driver side monitoring as a whole has existed for over a decade now. And I'll tell you what are the standard techniques they've used and why they're not relevant to when we move more towards autonomous driving vehicles. So the next one here I'm going to compare is a study done by Professor Missy Cummings at Duke University here. So another key reason why we want this technology is today's level of autonomy of driving. So what do I mean by that? So SAE, so the need for the technology is still where we are. The second portion of the need for technology is mainly to support the increased level of autonomy in the autonomous driving vehicle levels. So more and more we go, we have computer and humans are in the loop for driving. And on the right hand side, you can see here, this is the skill rule knowledge expert graph here. Primarily what they're showing here is the reasoning and decision making of humans and computers when we go more towards autonomous driving. Primarily, we are really good. We know what we, as humans, the skills that we need to maneuver the vehicle around. And we are really good at programming them using complicated rules and implement them through embedded system. And these vehicle technologies are good at following these rules. The interesting part comes here is the uncertainty part. Who makes the decision when we have situations like this? We all can see that this is a stop sign and the autonomous vehicle can see them and they will stop if they see them. But can you see this picture on top, which is a stop sign which is occluded and hidden? As humans, immediately when we see them, we know that, hey, that's a stop sign that's hidden. But for an autonomous vehicle, for today, commercialized vehicle to know them, there are studies and advancement by going humans come into play. And that's why we need to monitor the driver in loop. And on the right top corner, you can see that bottom corner, I would say that there's another scenario where we have a stop sign and the bunch of signs that say you cannot proceed in either direction. And if an autonomous vehicle is going to see this, it's probably going to stop there because it has to break the rule here. Now that's where humans come into play with the level of automation that we are talking about. Level 2 and level 3 is more or less like a gray area where we need a balance of human and computers together to make decisions. Okay, so continuing to that discussion, this is where it happens. So all these decisions have to happen seamlessly, and today this is broken in between the computers to make these decisions on the top and the humans to make these decisions in the bottom. We call top-down reasoning. So there needs to be a consistent and timely handover to the human when the computer cannot make these decisions. Now that's the reason, that's another key reason why we need to monitor the human being and make sure that the driver is alert and aware of the driving situation. So now I'll go over the comprehensive overview of driver state monitoring before going into the details of the implementation itself. We need to understand two key components as I introduced at the beginning. The first thing is the distracted driving behavior. Now, distracted driving is anything that diverts the attention of the driver. That includes talking, texting, eating, playing with any of the in-vehicle infotainment systems. So primarily anything that takes the attention of the driver away from the task of safe driving, overall considered as distraction for the driver. Now, how do we quantify these things? There's a whole bunch of metrics that we can go through, and researchers have shown that we can study these particular list of metrics that I in the table here to compare with psychological measurements of how the driver behaves in a certain condition. For example, we can see some of the driver's visual distraction through glance pattern. So glance pattern is essentially is quantified by finding out the area of interest of driver's gaze around the windshield, the driver's window side, or the front passenger window side. So technologies can segment all these things into different areas of interest and figure out where the driver is looking around, where the gaze pattern shows. That's basically the gaze pattern. The mean glance duration is something that how much the driver spends on all these areas of interest. And eventually we know the eyes off road duration. So if at all we know where the driver is looking around in the windshield area and the window side section, it's quite possible that the driver is distracted visually here. And similar way, we have this auditory and cognitive. So the pupil diameter is studied and it's considered as very sensitive to auditory distractions and cognitive distractions. Auditory distractions are anything that, for example, if your cell phone rings or is around your vehicle or anything that's blink frequency and pupil diameter are key measurements here. And same for the cognitive one, which is an example of any of us driving a vehicle and thinking something that happened at home. It's possible that we can detect those things through pupil diameter. And there's a lot of researchers that have gone through this thing. And the other one is the mechanical body posture of the driver. For example, if the driver is looking around the passenger seats behind or in the front, you can easily detect the head direction and orientation. So this is the entirety of the driver distraction behavior. The next one is the drowsiness. Drowsiness is essentially something that's like a neurological need for sleep, something that is not allowing the driver to engage in the driver continuously because of fatigueness is also referred as the same term. And some of the metrics that we use to detect them are eye-based, which is the percentage closure of eye, uh, mean square eye closure. So we have mean eye closure, average eye closures. These are some of the parameters that the engineers and psychologists came up. And also we can use blink frequency and micro sleep rate. There's a whole bunch of definitions here, but these are the primary metrics that we use to show whether the driver is drowsy or not. And the other ones are very common behavior based, yawning, slouching, and eyebrow rising. So these are the two key components. The distracted driving is detected by gaze pattern. The drowsiness can be detected mainly by the eyelid movements. Okay, some of the standard techniques that we have in the industry. The first one is the driver. I have a diagram here, as you all can see. Here, the driver is trying to drive in the road, and you can see that there's a pattern here where the driver is trying to balance the vehicle to keep in the center of the lane, but unfortunately, the driver is probably distracted, or maybe the driver is drowsy here. And you can see that it's possible that we can read the steering wheel information, steering velocity, and a whole bunch of other information from the steering wheel itself to understand how the driver is reacting to certain conditions. This is the most prominent technique that we have in the industry. As most, I would say, more than 70 to 80% of the OEM use this technique today. We'll talk more in details about this thing in the upcoming slides, but essentially we monitor the driver's steering wheel information and also the lane information of the where the vehicle is within the lane. Combined together, a complex model is developed. The next one is biometric sensor-based system techniques, where we get to measure the driver's heart rate, the driver's brain activity. We can read the driver's temperature and EEG and many other biometric related signals that we can read. And based on that, we can make some decisions of whether or not a driver is fit to drive the vehicle, and whether or not the driver needs a break. The third technique, which is the vision sensor based technique, is the most advanced technique that we have. It's getting these techniques into techniques, as I can see on the right hand side, uses some sort of way of detecting the user's facial features, expressions, the reactions of the human being, the eye movements, as I mentioned, the gaze and the eyelid, and a whole bunch of stuff. So that is those are a whole suite of technique that falls under the vision sensor based technique. And a lot of OEMs are trying to implement this technology. And it is a good time to be here and improving and designing this technique as we move towards more higher level of vehicle autonomy. So this is a full-blown view of a generic driver state monitoring system. What we see here is essentially a driver sitting in the car with these sensing units that essentially senses the driver's facial pattern. And this is one way of having the sensing unit located here, but there's more than one way of placing them in this sensor unit inside the vehicle and detecting different characteristics of the driver. We can see here that these sensing technologies can be either image-based, we can have different IR sensors, we can have other techniques of measuring what the driver is doing in the vehicle and process these information and come up with essentially where the eye gaze looks like and the facial landmarks, the 3D face position, the eye measurement, and a whole bunch of other information that can gather from the driver itself. And here we see that we can also get the steering behavior power steering technology that we have today that can provide so many information that we can read, and a generic control algorithm that uses all these information and makes decisions whether or not the driver is distracted and needs a time break, if the driver is drowsy or not. Eventually, all these informations are processed and provided back to the driver in the form of haptic seat vibrations, audio-visual alerts. These are different ways of alerting the driver when a potential imminent danger is coming. In recent OEM product lines, these are the most common way of indicating the driver. So these haptic seat warning vibrations are located in different positions of the seat itself. It can be behind the driver or it can be in the headrest. Sometimes these vibrations can be implemented in the steering wheel itself, because in some aspects the driver are also actually in the loop while holding the steering wheel. So there's different ways of alerting the driver, and this particular schematic shows a very generic means of how a driver state monitoring can be implemented. So now I'm going to go into the specific techniques we talked about. The first one I'm going to talk about is the driver steering behavior based method. The driver in this particular method, the key inputs are provided over here on the right hand corner. The first thing is the steering wheel angle. The steering wheel angle based measurements can provide a lot of details about how the driver reacts to certain conditions that shows the distraction and the drowsiness. It's very sensitive. Today's sensor allows us to be very the steering wheel angle. And the next input is the lane-based information. So this one is essentially sensors that detects where the vehicle is within the lane. Is it in the center of the lane, or is it away from the center by a certain lane offset? Is the vehicle touching the edges of the lane, or all those sorts of information can be gathered using so many different sensors we have in today's vehicle. We have a lot of techniques of way of detecting that. That is a second most important input. The third one is the road condition, whether the road is slippery or is it like the terrain has changed. For example, driver is driving on the road, suddenly he gets off the road or something. And other road conditions, potholes and other things that can primarily distract the driver while normal driving. So these are the three key inputs that are used to model a complex adaptive control system to make decisions based off of all these information, whether or not the driver is distracted. How they do that is essentially creating a map of all these parameters to something called a drowsiness reference from Karolinska Sleepiness Scale. So this is a university in Sweden that has been studying drowsiness of driver for years now. And Mercedes-Benz done a study with about 1.2 million kilometers of driving behavior based on different types of drivers, experienced, trained, experts. They came up with a complex model that all these inputs and the map of this under any of these particular scale while driving normally or while driving distracted. So in essence, this technique uses a lot of sensing information and it's a very complex adaptive model that uses all these inputs and correlates to the drowsiness scale that we have. It's very interesting and very complex, and it's more easily like implemented. That's why most of the OEMs today have this particular technique adopted and in the product line that we have, because we all these sensing that are needed are primarily available already to us in the vehicle, and that's nothing new to be developed. I will go over this particular one about Mercedes at the towards the end, where we talk about the state of the art technology.